Welcome again to Guild and to another Microservices meetup. We're always very, very happy to be hosting this meetup here. We've had some really, really great talks in the past, and I'm sure it's not going to be any different tonight. We have 2 talks. For the past meetups, I think we had 1 only, and tonight's going to be a bit different. We have 2. A couple of things first, I'd say. So pilots, if you haven't seen, it's here to my right. We have here at the back, if you haven't noticed. And Peter will be here at around 7:45, or thereabouts. So, our first speaker for the night, we have Paul Monney. Paul's going to be talking about microservices with .NET and RabbitMQ.
Great, hey. It's my first time here, so I'm going to get into this nice and slowly. So my name is Paul Monney. I currently work for Ryanair, and I've been involved with microservices for a couple of years now. So essentially, this talk is going to center around .NET and RabbitMQ. So effectively, by way of a brief overview, well, first of all, I'm not a microservice expert in any capacity, so I'm not here to preach or anything like that. As I said, though, I've been involved with it for a number of years, baptism of fire type thing, so I'm effectively here to share my adventures, if you like, so agree or disagree, as you will, as I go on, by all means. By way of a brief overview, what I'd like to cover tonight is, first of all, microservice design based on some real-world examples. There's no theory in this presentation at all. It's all practical stuff. Everything I'm going to talk about is actually running and working in production in some capacity somewhere. So I'm going to go through that in detail, and we'll focus on, but it won't be restricted to .NET and RabbitMQ. I'm talking to a couple of you guys there. Now there's a lot of Java, Scala, Ruby, and a little bit of Go here. So a lot of this stuff will still pertain to that. It can be abstracted out. There'll be stuff that's solely focused on those 2 technology stacks, but for the most part, it applies to any given technology stack within the context of microservices. And I'm going to briefly move into their design patterns then, specifically the design patterns that are, I suppose, form the fulcrum of microservices, decoupled middleware, circuit breaker, and then one interesting one called the Flyball Governor. After that then we'll move into some implementation problems that myself and my team have experienced over the years, which you might find interesting, and how we overcame them. First of which is consistent message delivery, and then load balancing a RabbitMQ cluster, which is not as straightforward as it may sound. Finally then, so that's all technical to begin with. I'll wrap up briefly then by going on to the softer side of things, which is selling microservices to the business, which is obviously, depending on who you are, where you work, can be a trivial or quite a tangible task. But basically I'll go through my experience in that regard, and hopefully it applies to you. So, as I said, to begin with design patterns, essentially the microservice architecture, the quintessential design pattern is the decoupled middleware pattern. In its simplest form, we have effectively, again, within the context of .NET here, we have an ASP.NET application which consists of a dispatcher, message dispatcher. The message dispatcher obviously dispatches the message to input queue based on a microservices. I've named this here Simple Math Microservice. My blog, I talk a lot about this stuff on my blog, and I always refer to Simple Math Microservice by way of example. A simple microservice that performs one function, which is to basically double any given number. So you'll see that a lot here, just in case anyone's wondering specifically what it is. In any case, Simple Math Microservice has 2 components, similar that mirror the ASP.NET model, which is a receiver to receive the message and a dispatcher to dispatch the result. So essentially the process flow is dispatcher on the ASP.NET side receives a request. That request is pushed into an input queue, input within the context of the microservice, and the microservice has a receiving component which dequeues that message and consumes it and processes it in some capacity. The message itself then will be processed, whatever business logic is in place will apply, and a result will then be output by a dispatcher to the output queue, which is listened to by the ASP.NET service. Okay, so that's suppose the quintessential, I'm not sure what the experience level here in microservices is, so if I'm boring people, just raise your hand and I'll move swiftly on. This is all fundamental stuff and a little bit more advanced, cool stuff, but if not, I'm just going to ease into it gently, as it were. So, straight off the bat, of course, people are probably thinking, well, hold on, I mean, it's not that simple, there's a lot more to it. I'll get to that shortly, but this is, I suppose, the canonical example. So, if we extrapolate that out a little bit, again, we've got microservice, still on the decoupled middleware pattern. We have microservice daemon, generally some sort of a self-contained process. Generally, for example, in a Windows environment, we're talking about an executable file, which is a Windows service. So again, here we are, we have a message dispatcher, message goes to queue number 1. That message is consumed by the opposing microservice, process dispatched across the service bus. Service bus obviously being the unit by which both microservices communicate with one another. So effectively, the decoupled middleware is all about shock absorption really, and it's all about interfacing two components or more than one component that were never meant to be interfaced before, so it provides a common level of abstraction in that regard. Generally, we experience generally they're asynchronous. So one of the great things I've experienced anyway, I'm not sure if you agree with microservices, is we effectively achieve parallelism to a great degree without having to dive into the complexities of applying parallelism in the various languages. You know, each one of these microservices runs within their own bounded context. They're effectively doing their own thing with their own OS threads and so forth, and we can achieve all of that without having to dive into the complexities of multi-threading and so forth, which is great. Okay, so that's about it for the decoupled middleware. I'm going to move swiftly on. Circuit breaker, the next, I suppose, quintessential pattern in terms of microservices. Again, we have a client, doesn't matter what the client is, initiates a request, and rather than go directly to our microservice, we have a filtering layer here, and a circuit breaker in the middle. The circuit breaker effectively counts requests that come in. So this request happens to be a request 1 of n, we'll say. What happens is the circuit breaker kicks in, and very simple logic is invoked, which is to say that if the request count is less than the threshold, so we have a predefined threshold, which is, let's say we want no more than 1,000 messages at any given time, or 1,000 requests per second through our circuit breaker. That request count there will be set to 1,000, such that if the request count is less than the threshold will be set to 1,000, such that if the current request count, if this will say request number 50, less than the threshold, it's allowed through and processed by one of the various microservice features as normal. If not, on the other hand, obviously the request count is greater than or equal to the threshold, so in this case we'll say greater than or equal to 1,000 messages, then that request will be rejected and handled in some graceful manner by the initiating, by the circuit breaker, and processed then in some sort of meaningful manner by the client. Okay. I mentioned briefly earlier the Flyball Governor pattern, so what the hell is that? The Flyball Governor is something that myself and my team come up with ourselves to facilitate a specific problem. First of all, a Flyball Governor, or centrifugal governor, is a mechanical instrument that exists in the real world that is designed in order to regulate the flow of any given fluid through any given mechanism. For example, there's one in your car to regulate the flow of fuel. Effectively how it works is, as you can see, there are 2 oscillating balls here, each one on extending arms, and what happens is, as liquid comes in here, it fills up slowly, and the oscillating balls are raised, the arms interlock until they get to a certain point where they lock completely, at which point the valve at the top here is closed completely, preventing any more liquid from coming in. Similarly then, as the liquid is drained from the bottom, the arms come closer together, and the valve is released, allowing more fuel. And the point being that you want, at any given time, some fuel coming in through the mechanism, but you don't want it to reach a certain level either. So, what the hell does that all mean within the context of microservices? Effectively, what we want to achieve with this, or what we've achieved in terms of, ultimately this all leads to auto-scaling. So, what we experience with the Flyball Governor pattern is the load never drops to 0% capacity, simply because As the oscillating arms go down, they always let more fuel in, or in the case of microservices, they let more messages through. So that will happen generally before 0%. So we never experience that. And similarly, we never experience load that rises to or above 100%. Now, when I say 100%, this is all predefined by the type of by your configuration. So, for example, as per the previous example, it might say 1,000 messages per second is 100% capacity in this case. And what we effectively achieve is automatic balance through polling, which I'll get to in a minute. Now, what this requires, though, in order to implement, requires detailed tuning to establish the optimal setting. The reason being, you don't really just plug this thing in and let it run and everything's going to be fine. You have to sort of, you have to determine what 0% is, what 100% is. Well, to be fair, 0% will generally be 0 messages, but 100% could be anything depending on your needs, requirements, hardware specification, and so forth. And as anyone who's implemented microservices will be familiar with, there's no plug and play concept really. Everything is heavily based on environments and so forth, and has to be rigorously pushed in order to determine optimal configuration settings. But the end result of the Flyball Governor pattern is that we achieve auto-scaling through a natural type of equilibrium. Basically, the microservice instances will balance themselves out and provide their own scaling as needed. So, let me just step through a quick, I suppose, abstraction from a design perspective. RabbitMQ has a management interface, an admin interface, and this admin interface provides key metrics in terms of RabbitMQ itself and its performance at any given time. So, for example, we can see the amount of messages coming in to RabbitMQ, the amount being published, the amount being processed, the amount being dispatched, the amount of messages that die, and so forth. Any metric really pertaining to messages coming into RabbitMQ is captured there. So, what we've come up with is a .NET library called QWatch, and effectively what QWatch does is it will poll the RabbitMQ management interface, which exposes metrics in JSON format. So let's say, for example, we've got any given queue. We'll say a queue called inbound queue, for argument's sake. We can poll that and get metrics pertaining to it at any given time. Those metrics tell us if the queue is either based on quality of service or QoS. If anyone's ever done message brokers, you'll be familiar with that term. Basically, QoS is something you want to achieve 100%. You want all your microservices to be running as near 100% of the time, as much as possible. Otherwise, you don't want them sitting there idle or you've wasted resources effectively. So, again, what QWatch does is effectively at regular intervals polls the RabbitMQ admin interface, pulls back information pertaining to all or any given queue you like, and will tell you basically whether or not the queue is being underutilized. So an underutilized queue, for example, might be a queue where there's no messages or very few messages coming in. What happens then is there's a chain of responsibility that's invoked, a chain of responsibility in terms of design patterns. So what will happen is a number of business rules will kick in. First of all, we'll say, okay, is the queue empty or is the queue full? Is the rate at which messages are being dispatched to the queue greater or equal to the rate at which they're being consumed by a microservice at the other queue? Obviously, if the microservice is consuming messages quicker than they're being put onto the queue, well, it's probably idle a lot of the time. Or conversely, if the microservice is backlog, if the backlog is building up and the microservice is pulling messages off the queue more slowly than they are being invoked and pushed onto the queue, well, then we probably need to scale out. So the end result of this is QWatch is that for each queue we get either a scale in or scale out directive based on those metrics from RabbitMQ. So our microservice, let's say microservice 1 here, is running as normal. It has an inbound queue and an outbound queue. It receives messages on the inbound queue and pushes results to the outbound queue, which are consumed by a client somewhere. The whole the design, or I suppose the key concept behind the Flyball Governor pattern is that each microservice has its own diagnostics queue. And that diagnostics queue is unique to the microservice and is known by QWatch. So, for example, if QWatch determines that, okay, well, microservice 1 here, there are 100 messages per second coming onto the queue, coming onto inbound queue, but the microservice itself, the dispatch rate or the consumption rate is only we'll say 50 messages per second. So in other words, 100 are coming in at any given time per second, or only 50 are going out, so we're experiencing backlog. So Microservice 1 is overcapacity, in which case there is a small service, a small listener running in Microservice 1 that's listening to diagnostics queue. QWatch has determined now that Microservice 1 is overcapacity, so it sends a scale-out message to the diagnostics queue. Microservice 1 has its own dedicated thread which is listening to diagnostics queue, consumes the message, and scales out appropriately. So when I say scale out, I mean these microservices in .NET are essentially, it's a Windows service that encapsulates the service itself, and there's a basic bootstrapper when the service runs that invokes at least one instance of Microservice 1. That microservice sits there and does work. So it's the Windows service itself that's listening to diagnostic queue, and if it determines that Microservice 1 needs to be scaled out, what it'll do is it will kick off a dedicated thread and a foreground thread from an operating system perspective and run another instance. Remembering that Microservice 1 itself is basically an infinite loop, okay? It's effectively sitting there listening to the queue, and because of the nature of this, again, there's no contention here in terms of resources, unless you're dealing with some sort of flat file or some sort of file system thing. If you're simply reading over a database or communicating with some downstream RESTful API, there's no risk of race condition or anything like that. So again, as I alluded to earlier, we experience, I suppose, the benefits of parallelism without the complexity. And as I said, QWatch is bound to all queues basically in the system. So effectively Microservice 1, 2 and 3 here, the same applies to all. QWatch determines, okay, inbound queue here, which pertains to Microservice 1, is under capacity. I'm going to scale that in, whereas it's over capacity. Inbound queue for pertaining to Microservice 2 is over capacity, I'm going to scale it out and so forth. What we achieve then is basically auto-scaling microservices that will scale out as and when needed in their own time without the need for manual intervention. Of course, the problem with that is we can't really trust the system to adequately scale out and scale in itself, because we may experience a sort of a bounce effect. I mean, for example, what happens if there's a hiccup in the network or some sort of delay where QWatch doesn't actually return anything for a couple of seconds, given some sort of TCP contention or something to that effect, and then all of a sudden it returns several metrics, one after the other, consistently within the context that are within, let's say, a very small time interval of one another. So it might say, okay, inbound queue here is over capacity, so I'm going to scale this out. As soon as we scale it out, then it goes, oh wait, now it's under capacity, you can scale it back in, out and in, out and in, I think we get this bounce effect. So again, with all things related to microservice, it requires extensive testing. So we need to define our interval here, we need to define how often we need to expand the queue, and we also need to define a percentage effectively, which is what QWatch does. QWatch also will allow microservice to say, okay, this queue, I'm Microservice 1, I'm listening to inbound queue, but I'm over capacity here, I need to scale out, but I'm gonna allow myself a threshold, we'll say 20%, 10%, 5%, whatever is deemed necessary. So in other words, what happened is it will say, okay, it's only about 5% over capacity based on the last run, so I'm going to leave it be because it's not too bad. Whereas if we start to get to 10, 15, 20, or whatever number pertains to your particular situation, then okay, now I'm interested. Now I'm going to scale out. So essentially, it does allow the developer I suppose the luxury of being able to, first of all, configure all this and how it's going to behave. It's not just a black box type system. Again, though, it does require extensive testing. And essentially, the Flyball Governor pattern is very similar to the decoupled middleware pattern, as you see here, but effectively what it does is it turns this into this. So, again, we have our ASP.NET application by way of example, dispatcher, input queue, and now we have multiple receivers, potentially, depending on the load, depending on how busy input queue is. And similarly, the dispatcher, we can scale those out accordingly as well. And we achieve then instances, so the client is none the wiser effectively, nor does any developer, DevOps engineer, or otherwise have to manually intervene at any given time. Incidentally, Flyball Governor, as I said in the beginning, is a mechanical instrument. Each one of your cars has one. It's also called a centrifugal governor. You may have heard the expression, right lads, we're gonna go at this thing balls out. Well, that's where that phrase comes from, effectively. It refers to the two oscillating balls on the arms of the Flyball Governor. Okay. So, from a C# perspective then, we can also express, or we can design microservices in terms of more traditional in-tier application structures. So for example, with our web browser here, as you can see, we've got a web server here, which is called Web 1. Not sure how easy it is to see that. I'll just run through it briefly. So we've got a message consumer, message parser, which depending on the format would be JSON or any other format. It comes in, the API itself, and then we've got our request mapper, where we need to obviously determine what the request is. So it's a request to get data, delete data, add data. That mapper has to be pointed to some sort of a function downstream to achieve that. And then we've got our dispatcher as well. So by way of example, if we step through this quite quickly. So the request comes in. In this example, I'm actually using Signal OR. So this is a Signal OR design. Again, this is in production running for a US education company. So Signal OR request comes into the API, processed over AMQP, RabbitMQ, and what happens is effectively the request is mapped to a specific function. The function is executed. The response message is parsed and built and pushed back to input queue, and then that response is sent back to one of the bigger part of this happens in the microservice layer. The response is then sent back to the queue, back to the API, and in real in terms of from a WebSocket perspective, then pushed back to the browser. So again, a more sort of I've been talking very abstractly here about some more some of the fancier concepts of microservices. So this, I suppose, is more of a fallback to a more traditional model. So I mentioned there that covers the design patterns section of the talk. I mentioned earlier that I go through some real world problems that my team and I experienced. So the first of two is consistent message delivery. How do you achieve consistent message delivery across AMQP, specifically with RabbitMQ? I mean, let's look at the problem first. So we've got our users here, ASP.NET application, messages come in at any given, I suppose arbitrarily based on however many users are currently logged on. So they're processed in by a simple Mac microservice, again by way of example, and the outbound queue then handles the messages that are consumed by the ASP.NET app and sent back to the user, which is all great in theory. But how do you control, for example, RabbitMQ, we don't have any guaranteed message delivery. So, as you can see here, I've just color-coded these so they can be visually represented. So I've got this blue message, which is the first message that comes in. Yet, as you can see, it's not the first message to leave. In fact, our red is the last message to come in, whereas the red message is the first message. And what have you? Ideally, what you want is the red message to come in first, but as you can see in this case, the green message here is processed last, whereas it should have been processed second of the three. So our ASP.NET application is going to have some trouble determining that, and user A may receive user B's response based on that. So, I mean, how do we tackle that to achieve consistent message delivery? Because bear in mind that the ASP.NET application is simply each worker process is effectively a thread that's listening to an outbound queue or a response queue. It doesn't know the difference with it. It's not aware of any other threads that are currently executing. So what we could do is, well, we could take we could have each process assigned to a specific queue. Because that sounds like a great idea. I mean, we've got three messages coming in here. Again, users, ASP.NET app, messages coming in 1, 2, 3. Okay, they're processed by the simple mat service in an arbitrary order based on how they're delivered. And we have, okay, now we've solved the problem here because ASP.NET app pertaining to user A, which sent in the red message, is listening to this queue here. Similarly, user B, blue message, this queue here, and user C, green message, this queue here. So we are only ever going to get the correct message per queue because they're predetermined, predefined. Of course, that all, again, in theory, is great, but not very practical because, I mean, if we have thousands of messages coming in, we can't very well invoke thousands of queues. And where do we stop? I mean, you know, we could say, well, let's just spin up a super large Amazon instance and have a couple of thousand queues, which is great. I mean, where do you come up with that number? And how do you manage that? And that means now you have to keep track of all those queues. Those queues are effectively tightly coupled to your application. And if anything happens to RabbitMQ or an instance, if it dies, for example, it comes back up, those queues are all dead now and they have to be reinstantiated, which is obviously a logistical nightmare. So it's not the most optimal solution. Not to mention the fact that, I mean, from a memory consumption perspective, you don't want to be creating a specific queue for every request. I mean, if every request that comes into an ASP.NET application creates a queue, which is effectively, obviously is a logical construct, but I mean, it's a very memory-heavy component in terms of AMQP, specifically RabbitMQ. So creating one on the fly is not what you want to do. It would be better if those queues already existed and were available for consumption as and when we need them. So the solution that we came up with was again the similar to the Decoupled Governor concept. That was invented incidentally. The Flyball Governor was invented in the 1800s by somebody smarter than me, so far be it for me to reinvent the wheel. Similar to this, how do we achieve consistent message delivery? We've come up with the concept of queue pool, which is very similar to a connection pool concept. Anyone familiar with database programming will know what a connection pool is effectively. It's in order to save memory, you have an in-memory construct which, as connections are created. So the first user logs in, gets a new connection. When he's done with it, that connection goes into a pool and is available for consumption by any subsequent requests. Again, all configurable. You can define the maximum length and so forth of a connection pool, and queue pool works in a very similar manner. So again, if we set through the process flow here, what we have is our user base here. Again, very the same as before, same ASP.NET application. Now, instead of the first step here, instead of just taking the message and pushing it onto a queue somewhere and expecting it to be consumed in a consistent manner somewhere, or dispatched to its own unique queue, for the previous example, the first thing we do is we go to the queue pool and we say, okay, I need a queue. I've got a request here and I need a specific queue. So what queue pool will do then is queue pool will go, okay, let's see. We have currently, one of two things will happen. It'll either say, okay, number one, we don't have any queues available, in which case I'm going to create a queue now and give it to you. Very same with a database connection. Now, if there's no database connection available, one is created, given to the user, and this queue is dedicated to that particular ASP.NET request, and no one else will use it. That is absolutely thread safe. So now, this request has its own dedicated queue, whether it was created or pulled from a pool. So now what we do is we fire off the message. Message comes down to RabbitMQ, is pushed through a queue, and comes down to Simple Math Microservice, which processes it accordingly. Simple Math Microservice is part of that message. The queue pool, the specific name of the queue will be embedded in that message, so Microservice will extract it out and push it to that specific queue. And again, a queue will never be used by any more than one instance at a time, any more than one thread from an OS perspective, or any more than one HTTP request from an ASP.NET perspective. Request now, let's say a very simple example. That user was the only user on the system at that particular time. Great. Okay, so he then his connection goes back into queue pool when the when the request is complete. User 2 comes in then and says, okay, I have a request here, I need a queue. Queue pool goes, okay, that's fine, here you go. You can use this one we prepared earlier. So essentially the first couple of users that log into a system are going to experience a slight delay as queues are created, but as queues are built up, subsequent users will experience actually greater throughput. Again, all configurable, so you can define your queue limit and so forth, depending on your hardware constraints and so forth. But so that's the queue pool concept, and we found it a very effective mechanism to achieve consistent message delivery across AMQP-based solutions such as RabbitMQ that don't guarantee message delivery or integrity necessarily. The last real-world example I'd like to talk through is load balancing or RabbitMQ and how we achieve it. You might think, okay, let's put a load balancer in front of it. Node 1, Node 2, Node 3, great. We've got a round robin or least con policy here, which is going to route messages appropriately. That's not actually the case with RabbitMQ. If anyone's in it, if you've worked with it before, you'll be familiar with what I'm talking about. What happens is, at any given time with RabbitMQ, there is a master node and 0 or more slave nodes. So you create a queue that's going to go on the master node. If you're load balanced, let's say the master node is node 1 here. So we created a queue called Q1, and our client application needs to use it, needs to push a message to it. So it hits the load balancer, but the load balancer, for whatever reason, decides to push to node 3. What happens is, it's node 3, then RabbitMQ will go, oh wait, that queue is not on node 3. In this example, beg your pardon, the queue exists on node 2, we'll say. So node 3, RabbitMQ goes, well, that queue doesn't exist on node 3. It exists in node 2, so I'm going to route you back to node 2. Now the client won't experience any error or any specific undesirable behavior, but under the hood there will be an extra network hop here, number 3 here in red, which is obviously not ideal because it will ultimately add to the level of overhead. So, I mean, what's the solution? Well, we can define it at an application level and say, okay, well, I'm gonna increment these or give them unique names. So I'll have, instead of Q1, I'm gonna have new Q1, new Q2, new Q3. I'm gonna explicitly install them or configure them on node 1, node 2, node 3 respectively. I'm going to ignore the load balancer, and with my client application is going to know exactly where they are. So, for example, by way of example, I have a randomizer here. The client application will go, okay, give me either node 1, 2, or 3. And the randomizer will randomize between the three, and will return a value of either new Q1, new Q2, new Q3, and then you'll be routed to the appropriate node, and there'll be no interference by RabbitMQ. So again, this requires your application to be cognizant of your underlying queue infrastructure, which isn't exactly from a design perspective a good thing. So we abstract it out to a queue metadata store. The queue metadata store is effectively a key, I suppose from a JVM perspective, a hash map or .NET, a dictionary or any other language. Effectively, it's a key value pair store, which stores where the queues are, what nodes they live on. So the client application will on startup basically pull a list of these back, or on demand pull a list of these back and determine, okay, I have a message here, it's going to Q1 and refer to the metadata store. I know that's on node 2, so I'm effectively going to go there, and as you can see, no load balancer whatsoever, whereas we can achieve balanced load across all our RabbitMQ cluster nodes without superfluous network hops, as per the first example. That covers the technical side of things for the moment, so I'm going to very quickly run through, because I'm conscious of time, I'm going to run through selling microservices to the business, if anybody is interested in that. Again, this is real world examples, none of this is abstract or theoretical. This is how, for example, we sold the concept of implementing microservice design to Ryanair and a big US education firm. So let's consider the old Monolithic Flow. So we've got our web application, it's a big monolith, black box, and effectively the client says, I want to book a flight. Okay, well, here are all the available flights. Okay, I want to book one of those flights, great, would you like to hire a car too, etc., etc., etc. The problem with this is immediately it's one-way communication, so the customer is in complete control. Effectively, the website is idle when the user is idle, so if the customer is sitting there doing nothing, the website is doing nothing either. So effectively, from a business perspective, we have a limited window of opportunity to interact with the user. We have to catch them on the fly every time, and hope, a user comes in, I just want to book a flight and I want to get the hell out of this website. We have to kind of hook onto that and go, oh, hey, look, do you want to book this and that and the other, and throw stuff at them when they probably don't want that to happen. So, I suppose the scope of opportunities to interact is very much reduced, which reduces then the potential for ancillary revenue, or revenue outside the concept of buying or selling plane tickets. From a technical perspective then, again, I found personally that one of the hardest tasks is also selling to engineers as well as selling to the business, for whatever reason. A couple of things we've gone through in order to, I suppose, soften the blow is, first of all, your monolithic architecture tends to result in dependencies. Failure affects everything. Big monolith, if it takes a hit and goes down, it generally takes everything with it. Of course, in practice that can obviously be absorbed and diffused, but it's not as versatile as microservices effectively. Change is slow, effectively, as we all know. Scale is relatively expensive, so minor feature, some sort of minor upgrade, update requires unilateral scale, requires a new build. The whole thing has to be redeployed generally, or at least one major part of it. steep learning curve. New developers that come in, they have to take apart the entire system, usually massive code bases. You're talking, for example, in the example of Ryanair, you're talking at least 10,000, or between 10,000 and 100,000 lines of code, all of which need to be learned, a big ball of spaghetti. Technology stack is then limited to specific skill sets. If you have a monolithic application that's written in Java, well, you can only hire Java people, or else people who skill set revolves around the JVMs or .NET and so forth. Whereas with microservices, obviously, that's not the case. You can deliver each microservice potentially in a different language technology, or if you like. One thing I've experienced as well, which I don't know where people are from here, but I spend half my time dealing with lawyers, and there's a lot of legal pitfalls, especially when you're dealing with large volumes of money. PCI and DSS compliance is, I suppose, the major bone of contention in that regard. You can't just write code as you would. There's a very specific process that has to be adhered to in terms of the code you write, how you write it, how it's logged, the deployment process, continuous integration, and so forth. And the rule of thumb is that if any given component has any sort of a direct, whether it be virtual or physical interface with another component that handles, for I suppose a simplistic example, is a lot of money, well, then that component comes within the context of PCI. It needs to be locked down, and development on a PCI-enabled component is very, very slow. So in other words, with monolithic application, everything is adjacent to one another. So effectively, if legal compliance applies to you, well, then it generally applies to the whole application. Whereas with microservice architectures, that can generally be abstracted out across bounded contexts and so forth. So other sections of the application can generally be developed, deployed, maintained, and upgraded outside the context of anything that may pertain to some sort of legal scrutiny. And finally, the monoliths, generally they're more rigid, they're likely to break under pressure, whereas microservices, again, generally able to absorb shock a little bit more efficiently. This isn't a general rule of thumb, incidentally, there are obviously monolithic applications out there that don't exhibit this behavior, but this is me selling to a lot of engineers that just don't want to take on this new challenge. By way of example, if we go back to a flight booking system, in this case Ryanair, we've got various microservices now. So we've split our monolith, which was a big ugly black box before, and now it's microservice based on flight, taxis, others, car hire, user profiles, hotels, fare finders, etc., etc. So now we've got our flight. Our user has asked for flight information, so we give it to them here. The flight microservice goes, okay, I'm interested in that. I'm going to send you back that information. Now, the flight microservice has pushed the message back to the queue. The taxi microservice has picked up on that message. He wasn't interested in that before, because the user just asked for flight information. Whereas now he's hold on, that user has just received some flight information. Okay, he's received flight information pertaining to Dublin to Heathrow, for example, or Stansted. Well, I'm interested in that. Maybe he wants to get a taxi to Dublin Airport, or maybe he wants to get a taxi from Stansted to wherever he's going there. So now I'm going to kick in and start pushing metadata to the client. Now car hire is interested as well. Hold on, now flight and taxi are interested in this, so I'm going to start pushing my stuff to the UI as well. Hotels, fare finders, other fares, and so forth, etc., etc. In other words, we've got effectively communication that's going on outside the context of the user's interaction. Remember, the users just asked for a few flights here. So flights kicked, that information has been returned to them, but now our microservice, without being invoked specifically by the user, are all kicking in and trying to sell the user things in real time. From a business perspective, the benefits we get of this are we effectively achieve two-way communication. So, as you can see now, the microservices are now responding without being asked. Incidentally, this does require some form of WebSocket or some sort of signal or slash type asynchronous communication mechanism on the client so that this information can be received and parsed and displayed on the UI as it's received. Again, business benefits, two-way communication, and we're in control. I mean, think about Google. Google take this to the, I suppose, the ultimate level, where they log every single event that you do. If you move the mouse in a specific way, it's logged. If you move the mouse up, down, left, right, if you tap the keyboard, pretty much every type of manual, physical interaction you have with your peripheral device, be it keyboard, mouse, touch screen, is captured by Google. They capture everything, and they use that to build up all their metadata about you. So effectively, gives them control, it gives them a great idea of who you are. And similar, that can be achieved, not to that scale necessarily, but microservices are, I suppose, a step toward that direction. The APIs as well, they're always working. I mean, if you think about a typical monolithic application, if no one's logged in, nothing's happening, or if people are logged in but they're only using specific elements of the system, you have a lot of dead weight, you have a lot of services that are wasted, resources underutilized, whereas our APIs could potentially always be working, always be computing. Every time a user does something, we can react to it in some capacity. I would encourage capturing as much information as you can as well. It might seem impertinent to begin with, but eventually, you might go through your Hadoop cluster or so forth, wherever all this stuff is going, and say, oh, well, actually, now we can, potentially use this stuff here, which we never thought about before, to monetize it, which is all great. But again, gives us a broader scope for ancillary revenue. From a technical perspective, to wrap this up, obviously we've eliminated dependencies to a greater degree. Failure can be isolated. One microservice dies, it can be isolated and not necessarily have an impact on its adjacent services. So as well, we can react to change quicker. If I skip quickly back, let's say we need to upgrade our user profile. Okay, well that can generally happen from a continuous deployment perspective outside the context of any of these services. So in theory, they can all still run while we're upgrading our user profile microservice. Which means scale can potentially be less expensive with the API scale individually, more intuitive learning curve. For example, I'm a new employee, just joined here, I come in, I've been asked to look at the user profile. Microservice is generally going to be a lot more straightforward for me to get my head around that than it would be if I were to dive into some sort of enormous monolithic code base that the guys who wrote it have been gone for 10 years. So we can also shield ourselves if we're I suppose savvy enough about things and they're going from the legal pitfalls potentially, and we effectively then have a suite of reusable components that are flexible and can generally bend rather than break under pressure. So just to wrap things up here, if I could offer any advice, again, I'm not an expert at this, but I've waded through the swamp, as it were, and any advice I can give is, first of all, log everything, and then log it again. Because when stuff goes wrong with these kind of frameworks, it's very difficult to determine what's actually happened, how to debug it, especially when the systems are distributed. Unless you have pretty decent logging in there, you're going to spend a lot of time with tools like WinDBG and into the garbage collector itself and so forth, use looking at memory dumps, which nobody likes to do. One other piece of advice I would give is if a framework exists, use it. There are plenty of frameworks out there now. We were talking earlier on, and we're talking about the Play framework. From a C# perspective, there's the Akka.NET framework and so forth. If it exists, use it, and try to avoid what you might refer to as the technical swamp. It's very easy to dive into all this stuff and think, oh, this is all great and cool. I'm going to tackle consistent message delivery, I'm going to tackle dead letter messages and so forth. Try to design up front from a minimalist perspective and grow it from there, Anticipate these problems, but don't over-engineer it, otherwise you'll end up in a world of hurt. Okay, so just to wrap things up then, again, my name is Paul Mooney, I work at Ryanair. My blog is insidethecpu.com. I've blogged about microservice extensively on that. If you're interested, if you want my blog, search for microservices. There's I have a dozen or so articles there. There's also, I don't have it up here, but there's Visual Studio magazine has a couple of articles on it. And my Twitter handle, Staishi Systems, that's me. And my GitHub profile, actually, there's a library up there called AMQP for C#. If anyone's interested, again, there it is there. And LinkedIn and so forth. I'll be around for a little bit after this anyway, have a beer if anyone's interested in chatting, but I don't know if we have time for a couple of questions. Great, yeah, so.
Great presentation.
Thanks.
I would just like to point out that in terms of scalability, especially for those with applications, I've used Azure Cloud Services with Azure queues that offer scalability out of the box. So you set up a service and you say, okay, what's this queue? and you configure how the instances will be multiplied according to that queue's load. Plus, the queues are not auto-scalable, so it fires out instances on the background, so the queue doesn't need any extra handling for load balancing or anything else.
Cool, cool. That's Azure Queue service, is it?
It's Azure Storage Services, and queues are part of that service.
Okay, cool. So basically what you're saying is I've wasted dozens of hours of work putting this stuff together for nothing.
It's not for everyone.
I'm only joking, yeah. No, that's great. Thanks very much. I'll certainly have a look into that. One of the reasons, I mean, I must admit, my team and I, when we put this stuff together back in the day, it was as much to learn microservices as it was to get working software to production. And the reason we went with RabbitMQ was because it's simplicity. I mean, you've got options like, we also looked at, for example, AWS, SQS and so forth, which offers similar auto-scaling features. The Microsoft, the Azure stuff, I don't think was out when we looked at it, but we certainly considered those options, whereas I think it worked out at something like $1 for every 10,000 messages on SQS. So we went with RabbitMQ simply because it was really easy. It was written in Erlang, you just click install, next, it's there, you have a lovely management information, and we all learned AMQP from it, baptism of fire-wise, but certainly, thanks very much, I'll definitely look into that.
Thank you.
Cool. Anything yourself?
The part we were talking about scaling out the microservices, you are talking about scaling out inside one host, inside one machine. It's like scaling the machines out, it's out of the...
Yeah, I beg your pardon, sorry, thanks for bringing that up, I should have specified that. Yes, talking about scaling out within the context of a single executable. So that doesn't actually scale out the machines or the hardware that it's running on, or the VM or anything pertaining to the hypervisor. It's specifically in Windows environment, a Windows service, and that service basically can scale out, each one running on its own dedicated thread. Again, the limit of that is depends on the hardware, depends on the load, depends on how the workload that the microservice has and so forth. But that all needs to be predetermined through stress testing and so forth. But thanks very much for pointing that out. Yeah, it's specific within the context of a single resource machine.
Thanks.
So you said you have essentially request threshold, and when you go over that, essentially reject requests. So first question is, how do you define that threshold? And second question is, why can you not just scale up your fleet before you reach the threshold in the first place?
Okay, well first of all, we determined that number again by stress testing. We're spending a lot of time with tools like JMeter, and what we generally tend to have is we know in advance, or at least when we built this stuff, we knew in advance how many users we wanted to cater for. So what we would do is we would start out with our baseline level of performance, which is what we absolutely needed to achieve for this thing to even be able for users to be able to log in. And we'd start that out on, the great thing about the cloud is it's great for sizing and stuff like that. So we started out on AWS with small instances. Then we have a baseline test for that, and then we work our way up with, we'll say 2 small instances, 2 medium instances, 2 large, and so forth. And then we go back to the beginning and we'll say, okay, now we'll try with 4. So we'd be able to determine at the end of it, okay, well actually having 2 medium instances is better than having 1 large, and so forth. So that's how we determined those numbers through trial and error effectively. So we'd be able to go to the DevOps guys at the end of the day and say, look, we need to procure 2 medium instances, 4 gigs of RAM each, etc., and we know basically that we have capacity to run. We'll say the sweet number we found was about somewhere between 50 and 75, maybe 100, any running instances of microservices within the one container. And then as regards your second question, then you mentioned scaling out the fleet. Do you mean scaling out the machines themselves, the VMs?
Yeah, before you even, if you know that that's your limit,
Sure.
so why can you not just add more hosts or more nodes or more VMs to handle even before, to handle the load even before you get to your threshold?
Great question, thanks for asking. Yeah, I should have gone through that as well. One of the things, this sort of pertains to the business side of things too, and selling to the business. The company I worked for, where we implemented this stuff first, they were absolutely not on board to go with this stuff. So one of the, I suppose, the sweetness for the deal was that I claimed that we could be ultra frugal with this stuff. We could save a lot of money. So the whole point was that this stuff ideally was going to work in Java, so that it could run on Unix, specifically because those instances are cheaper in the cloud. And effectively, I said, look, we can have potentially ultra small instances on Linux running here simultaneously, pushed to the absolute max without going over the limits. So operating within 80 to 90% of their capacity. So we can basically get our application will be, I suppose, down to within 5 or 10% of CPU capacity efficient in terms of, so we can reduce cost. And I think we reduced. I think the costs. I think they were 1/20th or something what they were currently costing to run. And of course, when the accountants and so forth, the finance people heard that, they were all over it. So it was more of a. There was as much a strategic move as well as a technical move in terms of. I wonder, can we actually do this before we start scaling out? So I suppose that's the most thorough and honest way I can answer that question.
So you said something about a connection pool of queues.
Yeah.
So the thing is, when you have a connection pool, you can test the connection to see if it's still alive, and it's not alive, return the connection to the pool. How do you handle the situation where, for some exception, the thread gets killed, and then you are not able to return the queue to the pool? Sorry.
Oh no, you're fine, thanks. I'm just trying to... I wrote this thing about 2 years ago, so I'm just trying to visualize the damn code in my head. There was... Oh yeah, there's an asynchronous event handler. One thing I would say about .NET is that it has, in this day and age, the latest incarnation has superb multi-threading and asynchronous handling. For example, it handles a lot of the stuff in terms of the CPU. It'll take... are you a .NET programmer?
No.
Okay, good. I see you nodding your head there. You're like, hey, yeah, come on, get on this.
No, I know that it's very good with asynchronous programming. And
Yeah.
It's a very good.
Yeah, so effectively we get a lot of that stuff out of the box. I did mention that the queue pool is thread safe, so no process is going to take the same queue out, and it's very easy to lock that down to apply mutually exclusive locks in .NET. And similarly, there is an event that fires in the queue pool pertaining to that queue, such that if the queue dies, a general exception is caught and it's returned back, and that queue will effectively be returned to the pool after a specific timeout occurs. Again, this is all on that GitHub repository. I'm happy to point you to the code afterwards if you like specifically.
Oh, perfect. Yeah.
Okay, cool.
Time for one more question.
Yeah.
Regarding the security and the resilience in terms of how you get the message back on the returning queue.
Yeah.
What happens if you don't? I mean, what happens with that queue? The failure, the service processing that message on the other end might just fail. You might just not get anything back. Right?
Absolutely. Let me just, for simplicity's sake, skip quickly back to that one. Yeah, here we are. So, so let me just see if I understand the question right. So, the request comes in, we get a queue from our queue pool, whether it exists or not, and the message is processed. The microservice gets the message with the queue name intact, and it goes, okay, he wants to send this message to queue 01, and what have you. But you said the message never gets sent out. Well, at this point, all of the microservice simply has an ID pertaining to the queue. It's not actually done anything with it yet. So if some failure occurs here, effectively no message will be sent out. So what happens is the only resource that's holding a lock on that queue at the moment is the ASP.NET app, because what it does is it invokes the message first of all, and immediately after invoking the message, it will take the queue that it's gotten from queue pool, and it will sit there and poll it continuously in the background until such a time that the microservice downstream here returns a message to it, and there's a specific predefined timeout associated with that polling. So if, for example, after 30 seconds no message has appeared on that queue, it's released back into queue pool. Cool, that's it. All right, no problem. Thanks very much.